Yep, that's right. You see, the big explosion only created the basic tenets of all living beings and heavy bodies in the universe. For 400 million years, the universe was plunged into darkness because, well, it's simple. There were no stars or galaxies. When that was rectified as clumps of gas turned into stars and galaxies, only then did the universe get out of its cosmic dark ages. So here's a little trivia for you guys. When do you think our solar system came into being if the universe was just darkness and eeriness for 400 million years? Well, our solar system was born 9 billion years after the Big Bang. So yeah, sorry sci-fi movies, there's a huge disconnect between the so-called explosion and scientific theory. And of course, this changes everything. The way things are, our universe still exists as a single inception point. It hasn't moved or expanded ever since the Big Bang. What really happens is that space has been stretching all along, and it carries matter with its trajectory. To put it in clear-cut words, the universe isn't expanding the way we visualize it or even understand it. It is actually the active stretching of space that precedes the expansion of the universe. We know it's a bit complicated to comprehend this, but it's also important to understand the implications of what we're about to tell you. For the purpose of this video, we continue to use the phrase the expansion of the universe to signify the active movement of our space, mainly because even scientists are comfortable using the exact framing to describe the recent discovery made by the James Webb Space Telescope. The fact that the universe has stopped expanding is both terrifying and inconsistent with our previous theoretical knowledge of this baffling phenomenon. So what do we make of it? Let's get right into that. To understand the scope of the implications, we need to go back to our existing studies of the universe. Back when the universe was born, aka during the Big Bang, our universe was smaller than a single atom. Ever since then, the universe has been stretching outward continuously. Initially, it expanded outward at unfathomable speeds, but as the universe grew older, it continued to expand and stretch out more. This is the moment that everyone thought would last forever after all. If the Big Bang was a beginning of sorts, we should expect a corresponding end. Our theoretical knowledge hence suggests that our universe is set on a singular trajectory of expansion without any plausible probability of a slowdown. In other words, we were sure of the ever-expanding nature of the universe, and that idea would have allowed us to figure out how and when the world would end. The James Webb Space Telescope shatters our preconceived notions of the universe's expansion. First things first. JWS has new study reveals that the universe has stopped expanding. The new images that the James Webb Telescope has received suggest that the universe's expansion has considerably slowed down. If anything, the universe may not be expanding at all. How exactly did this discovery come about? Well, with the recent images, scientists have revealed that the light waves have been seemingly bending as they have traveled through space. In time, the very bending nature of the light indicates that it is the space that has stopped expanding. The new images reveal something that is far beyond what the Hubble Space Telescope has achieved. Our previous knowledge was based on Hubble studies, and hence it didn't reveal the most important aspect of the universe. The new images have shown that the universe is essentially curved. The mind-boggling discovery therefore shows that the universe is a sphere, and our very existence, including space and time, is wrapped inside the sphere. With this, another major breakthrough is the light that has reached the new telescope, and the more we look at the images, the more proof we have that the Big Bang theory is both true and outdated. It is true because the universe began at one point and it has been ever expanding, but at the same time it is outdated because the expansion of the universe has been largely debunked with JWS's new data. If we study the data, we see that the universe, aka the spherical point, has stopped expanding, and that very characteristic of the universe hints at the most plausible fate of the universe. UN's end. As we said, the universe was created with a Big Bang, but we have never stopped to wonder what would be the exact nature of the universe when it ends. Scientists have revealed the possibilities of how the world ends, and spoiler alert, it's going to end the same way it began. The expansion has stopped, and what happens next is that the stretching of space would also slow down. The new data also reveals the plausible end, which is the big crunch. We know it's too much for anyone to wrap their heads around, but JWS is allowing scientists to observe the mechanisms of the universe. By doing so, we are now aware of the universe's trajectory. Instead of accelerating the expansion, the universe has stopped expanding, and hence, with time, this curve or the sphere that holds our universe would gradually collapse. This theory isn't new to scientists, but it's only with the James Webb Space Telescope that we have the evidence to confirm it. Imagine it as a full circle. Our universe has reached its peak of expansion, and soon enough it would start collapsing on itself. This collapse is the end of the universe as we know it. The James Webb Space Telescope is an amazing creation that is paving the way for how we understand the universe. The latest images from the telescope reveal that light is bending at the edges, which means our universe has stopped expanding, and it also means that we're closer to our ultimate end than we thought. Whether this is going to happen in the next few centuries or a few thousand years is anyone's guess, but for now our knowledge of the universe has reached an unfathomable stage, which by the way is pretty terrifying. The concept of the universe's expansion and its eventual fate has fascinated humanity for centuries. From ancient philosophical debates to modern scientific exploration, our understanding of the cosmos has evolved dramatically. The prevailing model, originating from the groundbreaking observations and theories of figures like Albert Einstein and Edwin Hubble, posits that the universe began with a cataclysmic event known as the Big Bang. This event marked the birth of space and time itself, propelling matter outward and setting in motion the cosmic journey we continue to unravel today. One of the pivotal observations confirming the expansion of the universe came from Edwin Hubble in the early 20th century. By studying the light from distant galaxies, Hubble discovered that these galaxies were moving away from us, and crucially, the farther away a galaxy was, the faster it appeared to be receding. This relationship between distance and velocity is encapsulated in what we now call Hubble's law, which serves as one of the cornerstones of modern cosmology. Building upon Hubble's foundational work, scientists have since refined our understanding of cosmic expansion through advancements in technology and observational techniques. Satellites and telescopes like the Hubble Space Telescope have provided increasingly detailed images and data, offering glimpses into the early universe and refining our estimates of its age and composition. The discovery of cosmic microwave background radiation, CMB, in the mid-20th century provided another crucial piece of evidence supporting the Big Bang theory. The CMB is a faint glow of radiation that permeates the entire universe, originating from the intense heat of the early universe when photons decoupled from matter. This relic radiation allows astronomers to peer back in time to when the universe was only a few 100,000 years old, providing insights into its early conditions and confirming predictions made by the Big Bang theory. Advancements in technology, such as the development of next-generation telescopes and space probes, promise to revolutionize our understanding of the cosmos in the coming decades. Projects like the Square Kilometre Array, SKA, a radio telescope array under construction, will provide unprecedented sensitivity and resolution for studying cosmic phenomena such as black holes, pulsars, and the early universe. In parallel, efforts to explore our own solar system continue to yield remarkable discoveries. Missions to Mars, such as NASA's Perseverance rover and the ESA's ExoMars program, seek to uncover evidence of past or present life on the red planet. The study of icy moons like Europa and Enceladus has revealed subsurface oceans that could potentially harbor microbial life, expanding the search for life beyond Earth. The intersection of astrophysics, cosmology, and planetary science represents a frontier of exploration and discovery. By studying the cosmos on scales ranging from subatomic particles to the entire universe, scientists aim to uncover the fundamental laws governing the universe's origin, evolution, and ultimate fate. Each new observation and discovery brings us closer to unraveling the mysteries of existence and our place in the cosmos. As we continue to explore the universe, both with our eyes turned outward and our minds probing inward, the quest for knowledge remains a driving force of human curiosity and endeavor. From ancient myths and legends to cutting-edge scientific inquiry, our understanding of the universe has evolved, shaped by observation, experimentation, and the relentless pursuit of truth. The idea of a big crunch hinges on the density of matter in the universe. If there is enough matter, the gravitational pull of all objects in the cosmos could eventually overcome the outward expansion driven by the Big Bang. This scenario would lead to a contraction of the universe, culminating in a reverse of the cosmic expansion and potentially ending in a singularity similar to the Big Bang itself. However, recent observations have suggested a different future for the universe. Data from the Planck satellite, which mapped the CMB with unprecedented precision, indicates that the universe may not contain enough matter to halt its expansion and initiate a big crunch. Instead, the universe's fate might be one of eternal expansion, albeit at an ever-slowing rate as dark energy, a mysterious force driving the universe's accelerated expansion, continues to dominate. Dark energy remains one of the greatest enigmas in modern physics. Proposed to explain the observed acceleration of cosmic expansion, dark energy is thought to permeate all of space, exerting a negative pressure that counteracts the gravitational pull of matter. Despite its profound implications for the universe's future, the nature of dark energy remains poorly understood, with theories ranging from a cosmological constant to dynamic fields evolving over time. The implications of an eternally expanding universe are profound. If the universe continues to expand indefinitely, galaxies will eventually become so distant from one another that they will no longer be visible from Earth. Stars will burn out, leaving behind remnants such as black holes and white dwarfs. Eventually, all stellar objects will fade away, and the universe will enter a state of cosmic silence and darkness, known as the heat death. The heat death scenario paints a stark picture of the far future, where entropy reaches its maximum and the universe approaches a state of equilibrium. In this state, no further energy exchanges occur, and all thermodynamic processes cease. While distant in time, the prospect of heat death raises philosophical questions about the ultimate purpose and fate of the cosmos. Beyond the physical fate of the universe, cosmologists are also exploring the broader implications of cosmic evolution. The emergence of life and intelligence in the universe represents a profound mystery, intertwined with the conditions that allowed for the formation of galaxies, stars, and planets capable of supporting life. The study of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments beyond Earth. The search for extraterrestrial life remains a central goal of astrobiology and space exploration. While no definitive evidence of extraterrestrial life has been found, ongoing missions and advancements in astrobiology continue to push the boundaries of our understanding. The discovery of extremophiles on Earth, organisms capable of surviving in extreme environments, has expanded our notion of where life might exist beyond our planet. Advancements in technology, such as the development of next-generation telescopes and space probes, promise to revolutionize our understanding of the cosmos in the coming decades. Projects like the Square Kilometre Array, SKA, a radio telescope array under construction, will provide unprecedented sensitivity and resolution for studying cosmic phenomena such as black holes, pulsars, and the early universe. In parallel, efforts to explore our own solar system continue to yield remarkable discoveries. Missions to Mars, such as NASA's Perseverance rover and the ESA's ExoMars program, seek to uncover evidence of past or present life on the red planet. The study of icy moons like Europa and Enceladus has revealed subsurface oceans that could potentially harbor microbial life, expanding the search for life beyond Earth. The intersection of astrophysics, cosmology, and planetary science represents a frontier of exploration and discovery. By studying the cosmos on scales ranging from subatomic particles to the entire universe, scientists aim to uncover the fundamental laws governing the universe's origin, evolution, and ultimate fate. Each new observation and discovery brings us closer to unraveling the mysteries of existence and our place in the cosmos. As we continue to explore the universe, both with our eyes turned outward and our minds probing inward, the quest for knowledge remains a driving force of human curiosity and endeavor. From ancient myths and legends to cutting-edge scientific inquiry, our understanding of the universe has evolved, shaped by observation, experimentation, and the relentless pursuit of truth. In the grand tapestry of cosmic history, each discovery and revelation adds a new thread, weaving together the fabric of our collective understanding. Whether contemplating the birth of stars, the collision of galaxies, or the fate of the universe itself, we stand on the threshold of a new era of exploration, poised to uncover the next chapter in the epic saga of the cosmos. In the quest to unravel the mysteries of the cosmos, scientists are also exploring fundamental questions about the nature of space and time. The concept of space-time, introduced by Einstein's theory of general relativity, revolutionized our understanding of gravity and the fabric of the universe itself. According to general relativity, space-time is not merely a passive stage on which events unfold but a dynamic structure that can bend, warp, and curve in the presence of mass and energy. One of the most remarkable predictions of general relativity is the existence of black holes, regions of space-time where gravitational forces are so intense that nothing, not even light, can escape their grasp. Black holes form when massive stars undergo gravitational collapse at the end of their life cycle. These cosmic behemoths continue to fascinate astronomers, offering insights into extreme physical conditions and the interplay between gravity and quantum mechanics. Recent advancements in observational astronomy have enabled scientists to study black holes in unprecedented detail. The Event Horizon Telescope, EHT, a global network of radio telescopes, captured the first-ever image of a black hole's shadow in 2019. Located in the center of the galaxy M87, this supermassive black hole's shadow provided direct visual evidence of the event horizon, the boundary beyond which nothing can escape. Studying black holes not only illuminates the nature of gravity and spacetime, but also offers clues about the formation and evolution of galaxies. Supermassive black holes are thought to reside at the centers of most galaxies, including our own Milky Way. Their gravitational influence can profoundly affect the surrounding stars and gas, shaping the galaxy's structure and evolution over cosmic timescales. Beyond black holes, cosmologists are also investigating the mysterious nature of dark matter and dark energy. Dark matter is believed to make up approximately 27% of the universe's total mass energy content, yet its composition remains unknown. Unlike ordinary matter, which interacts with light and other forms of electromagnetic radiation, dark matter interacts gravitationally and appears to be invisible to conventional detection methods. Dark energy, on the other hand, is hypothesized to account for approximately 68% of the universe's energy density. Unlike matter, which slows the universe's expansion due to gravitational attraction, dark energy accelerates the expansion, driving galaxies apart at an increasing rate. The discovery of dark energy's existence in the late 20th century was a profound revelation that challenged existing cosmological models and underscored the need for new theories to explain the universe's accelerated expansion. The interplay between dark matter, dark energy, and ordinary matter remains a central focus of cosmological research. Projects such as the Large Synoptic Survey Telescope, LSST, and the Euclid mission aim to map the distribution of dark matter and probe the nature of dark energy through large-scale surveys of galaxies and cosmic structures.